in this problem, we want to use the right-hand rule on this moving conductor. So you want to point your pointer finger in the direction of motion of the object. So I'll try to draw that here. All right, so this is going to be my right hand pointer finger. All right, so we'll point in the direction of velocity of the bar. And then our middle finger has to point in the direction of the magnetic field. Middle finger goes up. And in this orientation, the thumb points out of the page toward us. And then we can have just some other fingers behind it. Alright, so that's the middle. And this is the thumb. Okay. The middle is the B field. And now the thumb points out of the page. So the thing that's a little new here is the force is along the direction of the conductor. That means that charges inside the conductor are going to want to flow. They're going to want to move. And they can only really go so far, though, in this situation, because there isn't a complete loop. In order to keep current going as this object moves, it would have to make a circuit. It would have to have a complete loop. If you have a break in the loop, or there is no real loop involved, then what's going to happen is just charge is going to accumulate at one end. And it'll just stay there, It takes time for this to happen, of course, so there's going to be a transient flow of charge where the charges separate, and it really polarizes the conductor. Okay? But we'll see cases here shortly where there can be a current created. But anyway, the mathematics of this is there's a formula for it. The induced voltage in a object that's moving, like a conducting object that's moving in a magnetic field, will be given by the formula BLV. Okay, now that would be just the magnitude of the voltage. Okay, so let's see what numbers we have for our situation. We have a B field of 2.1 Teslas. The length of our conductor here is 5 meters. And then they give a speed of it being 0.67 meters per second. Alright, so we should just multiply those. Let's see, so 7.04, and the units will be volts. Alright, so as that object moves, we're going to have a potential difference of 7.04 volts between the ends of it. Now, since these rails here are metal, from what we've seen in the past, the charge is going to spread out along these rails. because they're conductors and they're in contact with a point that is 7 volts higher than the other point, then we'll maintain that potential difference throughout the whole conducting rails. So I'm going to put 7.04 here, and I'll say that the end of the bar that's at the higher potential is the end coming out of the page.